Bro, I need to start
Let's
like
see.
doing at least like what the site. I don't have time. The only thing I'm really not. It's fine. The yeah, you just.
Okay, so I'll post between tomorrow and Friday the solutions to the exam and also like the practice exams for the second midterm in case you want to check it out. If like during during the spring break. So kind of still a bit early, but like since like the spring break is kind of in the middle, maybe it's better for you to have it then together with the study guide. So essentially, like the second exam is everything that we have covered so far, plus very small things about double integrals integration that will start after the break. So it's mostly about derivatives, so the bulk will be kind of like on this stuff, chapter 14. But yeah, there will be some minor things on integration. So today, to try to finish this chapter, what we have to do is talk about two topics. So the first one is absolute max and absolute mean, which is actually pretty straightforward. And the second topic is Lagrange multipliers, which is a little bit trickier, but I mean, I guess not as bad, let's say. So let me just remind you like the situation in Calc 1 for absolute max and mean. So what happens here is what occurs in Calc 1 is that you have a function, right? A continuous function, and then you're looking at this continuous function on a closed interval. So maybe, okay. So like the function may have may have been defined for all numbers for all values of x, or it could have had like bigger domain, but you only care about like how the function behaves on a small set or a small interval, which is this fine. Like the important thing is kind of closed, but rather like really that it's finite. So you have like this interval, and then you want to find the absolute max and the absolute mean. So what happens is that, like just kind of like in the picture, as you can see here, it looks like the mean, like, if you had ignored the stuff about the domain, there would have been like at least like some sort of like local mean here, right? So you would have found a mean in at this point, but the thing that happens when you restrict the function to, a closed interval is that that forces it to take a maximum value and a minimum value. So, more pictorially, what's occurring here is that by putting these restrictions on the domain, it's kind of like as if you lift like a vertical wall at A and at B, right, which cuts the graph of the function. So when you cut it, yeah, they're like, in this particular case, like the function could have kept growing, but the fact that you limited its growth means that it will assume a max, right? So in this case, like the max will happen here, right? But it could have also possibly happened at the other endpoint, right? So usually, what I'm trying to say here is that when you were trying to find like absolute max and absolute mean um, of a function in a domain, in a closed interval, what you would do is like try to find like the regular mean and max of the function inside the interval. But you also then have to look at the endpoints, because now at the endpoints there might be artificially. Oh my God, I'm glad that we came before like it's raining like crazy now, because now it's really bad. So like because by restricting the domain of the function, you can kind of create artificial max and artificial mean, right? Because like again, the function could have kept growing, like you're restricting it, and so that's essentially what will happen in our situation. So, like the idea for us, I'll write the algorithm in a moment. of what you're supposed to do. Like, it's like, let's say that you have a function of two variables. And, okay, so what's the analog of a closed interval for a function of two variables? Well, the most like direct analog would be kind of like a rectangle, right? But the method is actually good enough, like it would also work with triangles, like discs. What really you need is like a finite region on the XY plane. The thing is like finite regions on the line, they're not that like they're not too interesting. They're mostly like intervals, if they consist of a single piece. But if you have something on the plane, then yeah, like there are many regions of finite size or finite area that you could draw. So let me just try to draw something that's not completely crazy for the picture that will try to make. So let's say that you have like actually let me draw something which looks a little bit more um which looks like has corners. So let's say that you have like a triangle. So maybe you have a triangle on the plane, including the inside. So like sometimes called like a solid triangle. And then you have like the graph of a function of two variables. So let's say. Okay. So what happens here is like kind of similar. Like I'm trying to draw the you know, your like the graph can extend like for like in a very top of like above like a very large region of the plane, but you only care about the part of the graph that's exactly on top of the triangle, right? So it sits above the triangle, kind of like in the same way that here you're just looking at the graph that's part of the graph that's above the interval. So if you were to try to find the max and the mean of the graph on that region, okay, so there could be like some max that occur already inside the triangle, right? So I'm trying to draw this like it looks like a max. And if I did it correctly, like, that point already happened to be inside the triangle. So this would have been kind of like located by the methods that we did last time of finding the critical points and finding the max, right? But the point is that because now you're looking at the stuff above the triangle kind of like will create like these walls that cut the surface or the graph into. So you kind of actually only care about the stuff, you know. Let's see, how should I draw this? Oh, this is actually a bit tricky to draw. But what I'm trying to say is that you only care kind of like about the region that I am coloring in yellow because it's kind of like the stuff that sits above uh, the triangle. And so now it is possible for like a minimum to occur somewhere in here. For example, a minimum to occur like maybe the lowest point now will be here, right? And if you, let's say that's presumably the minimum. And if you look at where the minimum happens, like what occurs is that now it can take place along one of the edges of the triangle, if that makes sense. So like the difference like with what we were doing before is like now when you add like these restrictions to the domain, then you can kind of create like artificially max and min because again, you're restricting the growth of the function. Okay, so to find what this is saying is that to find the absolute max mean of a function is defined on a solid finite solid region of the plane. There's so basically there uh two things that you have to do. So you have to find like the ordinary, like you have to find a critical point of the function that belong to the region that you're analyzing. So find the critical points inside the region you're studying. So this is kind of like more or less the same as what we were doing last time, finding critical points. Um, the second thing that you have to do, which is a little bit new, and that's kind of like the analog of evaluating the function at the endpoints, is that the endpoints in this situation corresponds to the end of the interval, right? What is the end of the solid triangle here? The ends are like the edges of the triangle, for example. So what you have to do is find the critical points of the function along each edge of the region. So find function along each edge of the region. And that includes, you know, this includes like the vertices of the region, or like includes corners. Well, let me put this like I'll put it as a third step. Like I'll just do this at the third step. And then you make a table, and then you make a table which it looks like this. So you put so you're going to make a table that has like the critical points from part one. So let's say critical points of one. And then you evaluate the function at each critical point from that from part one. Then you do the same for the critical points from of part two. And then you evaluate the function at each critical point of part two. And then you also have to add the the edges. Sorry, not the edges, but the corners or like the vertices of the triangle. Well, what in this case a triangle. And the example I'll do is kind of like the intersection point of the different edges. So let's say the intersections of the edges. Okay. So there are like three types of points that you have to analyze, and then after you do that, what you'll do is select the max value, select the point which give the max and mean value for f. And that will be the absolute and the absolute max and the absolute mean. Okay. So just as a note, which just finished time, this at no point do you have to use the second derivative test for this type of problem. So second derivative test is not necessary here.
Did you explain the last, how did you look at like?
So the thing is, like, for example, like, will become clear in the one that I'm about to do, but like a triangle like has three edges, right? So you would have to study the function along each edge, which again, I'll do in the example that follows. But then, so the edges, right, like the sides of the triangle meet at the vertices, right? So what condition three is saying is that you should throw in the vertices as potential places where the point, like, where the max and the mean can occur. So sometimes people will include that into part two, but it's kind of better to have those separate. So what I'm saying is that, like, what we have to look at are regular critical points that we would find like as last time, plus the critical points that occur along the edges, which is kind of new. Like that's something you have seen in Calc 1. So I'll show you how this looks like in this case. Plus the analog of the endpoints, and the analog of the endpoints are kind of like the vertices of the triangle, if that makes sense. But yeah, it kind of, it sounds more confusing in theory than in practice. Once you see it in practice, it is a bit more clear what you need to do. But yeah, when you write it on the board, it's, yeah, sounds more tricky. So, yeah, like I'll do an example in a moment, but before maybe moving there, like, is that okay? Anything else? Okay, so let's just, okay. So here, let's try to find the absolute max and mean. Absolute mean of the function inside inside the region determined by the curves. Um, so let's try to think about this. So, like, the important thing in this type of problem is just to have like an understanding of the peak of the region on the plane. So, like, again, like for all these problems involving functions of two variables, usually you don't have to think too much about the graph. It's more important to think about like the part of the domain that you're studying. So in this case, so what do we have in this case? Let's see. So you have this equation, which is the equation of a parabola, right? So it's a parabola concave up, like just has been shifted one half downwards. So it looks like this, right? And then you have the line, which is just a horizontal line at height one. So I guess like, is that making sense? So the region that I'm talking about, we're looking at the stuff inside, determine, like if you think about this as a sort of maps that you're drawing on the plane, we're looking at the stuff determined by these two borders or edges. So let me color it, but like use like a very small, like a very subtle coloring so that it's not, doesn't look like a mess. So the region on the plane that I'm referring to is like the thing that I just colored in white. And the idea is that if you draw that on the XY plane, then you have the graph of the function, right? Like this function is kind of like the standard paraboloid. So just imagine placing like the paraboloid on the plane, right? Like you have like your cup, you put it here on the plane, and then you're asking what's the max and the mean of this paraboloid above this thing, which doesn't have like a particular name. Is that making sense? So we're again, we're kind of limiting the graph to just lie within those within that region. Like so, doesn't matter what the graph is doing outside this region. You only care about what's happening. Is that okay? So let's okay. So let's just find out these critical points that I'm telling you about. So step one is the critical points of F inside the region. So let's just find the regular critical points. So what are the critical points of F? So we have to, like, you remember, like, critical points requires both, like, both partial derivatives to be zero. These functions typically are very easy because the problem is a bit long. So finding the critical point shouldn't be that hard. So like the derivative with respect to x is 2x, and the derivative with respect to y is 2y, right? So the only way for these to become zero, both equations, right, is you need 2x equals 0 and 2y equals 0. So there's only one critical point, right, which is the origin, right, in this case. So like the only critical point of F which is 0, comma 0. So that is the first step. Just find the regular critical points. Is that okay? The first step? Now comes the more interesting thing which you haven't done before. At least not in top one, and probably I don't think we have seen it before. So now we have to analyze the function along each edge of the region. Okay. So what do I mean by edges here? I just mean like, if you thought about this picture like as the map of a country, I'm just talking about the borders of the country, right? So like there's one border which is like along this parabola and another border which is part of the line. Okay, so like it has kind of like two main borders. So let's think first about this one is a little and also let me draw the critical point. So the critical point that we just found is the origin. So let me put it here in pink. So one of the points is there. Then we have to look at the edges. So the first edge is y equals x squared minus 1/2. So okay, so what happens with that? If you restrict yourself to that edge, what that means is that y is determined by x, right? Because like you are like moving on this along this curve, which has that formula. So what that means is that the function f, right, which is x squared plus y squared in general, now becomes x squared plus y squared, but here you can put like the formula for y, right? Okay, so that means that along this edge, the function looks like how? So this is x squared. Here I'm going to use the difference of square formula. So this is x to the 4. Okay, then there's like -2, the product of these two numbers. So you get minus x squared plus 1/4. Okay. So this just gives you x to the 4 plus 1/4. Okay, so what I'm trying to say is that the function is always this, like this is always a function. It's just that if you evaluate it along the edge, y kind of can be replaced in terms of x. And so like the function becomes like a function exclusively of x. Is that making sense? And so now as a function of x, now this is like, again, like a calc one problem. It has critical points. So how do you find the critical points of this function? Well, it's just like the derivative with respect to x, because that's the only thing that is left, right? Like the only thing that's left is like the x variable. right? And when critical point is when the function, like the derivative is zero, that's still like the same, right? So this is zero whenever x cubed is zero, which is x equals zero, right? Right? So that means that x has to be zero, but now what can you say about y? So if x has to be zero, what's the corresponding y value? Well, it has to be, we're working on the edge. So the edge is a parabola. So now when x equals zero, the corresponding value in the parabola is negative 1/2, right? So y is x squared minus negative 1/2 minus 1/2. So like you get minus 1/2 in this case. So what I'm trying to say is that the critical point that you find from this edge is 0, negative 1/2. So is that making sense? Questions about this? So I'm just saying, like, what you do is evaluate the function along the edge to turn it into a function of one variable, and for to that you find the regular critical point. I'm about to do it for the other edge, so like you see it again, but it's always the same procedure. Okay, so what's the other edge? The other edge is y equals 1/2, right? And now the function, we can redo what I just said. So f is x squared plus one y squared. That's always true, but along this edge, y is 1/2. So this becomes x squared plus 1/4, right? Because you're squaring y. So along the purple edge, like the function is a function of one variable, and now it has regular critical points, like and again, when is this going to vanish? Whenever x equals 0. But x equals 0 and y has to be 1/2. So that gives you another critical point. Sorry. Yeah, that gives you another critical point, which is 0, 1/2. So critical point. Is that making sense? So what I'm saying is that these are the first two steps of the table. Like we just did step 1 and 2. The last thing is that you have to consider the intersection point of the edges. So it's kind of like the vertices of a triangle. What are the intersection point of the two, like edges? Like they are like these 2 points, right? So you have to ask what are the values for these 2 points? Well, it is precisely the intersection. So that's when both equations are satisfied simultaneously. So this is when 1/2 equals like, x squared minus 1/2. So x1 equals x squared. So x is plus or minus 1. So there is an edge here, which is, negative 1, 1/2. And another edge, which is 1, 1/2. Okay, so these two corners, like if you want to call them that, is would have those particular values. And so what you have to do at the end is make a table with all the points that we found. 1, 2, 3, 4, 5. So we have 5 points, and then you evaluate the function at each of those 5 points, and the max and the mean are just whatever like give you the largest and smallest value. So I guess I can like let me write the first steps here because I already did those. So what I'm saying is that now you make a table. Where you put like the function together with its value. So let me use like the corresponding color. So when it's 0, 0, the value of the function is just 0. That one is easy to figure out. Well, obviously I chose like all the numbers so that they would be nice, but like in general, like in practice, like you can expect that because otherwise it takes a little bit, like you can see that it takes a while to do all the steps, so. Then the zero equals negative, 0, negative 1/2, that gives you value, 1/4, right? And then, the purple one gives you. This one gives you also 1/4, and then you have the corners, right? So the corners are -1, 1/2. That would be 1 plus 1/4, right? When you add the function, so it's 1 plus 1/4, that's 5/4, right? So this is. Right? So those are the functions, with the five, values. And so what is the smallest value? Mm, I guess the largest values, the max occurs at two different points. Those are, those are the mean and the max. It's okay, is that making sense? And every single, like, that's what I was saying, like, in this exam, kind of every single problem is solved exactly the same way. What changes is that the function, like, for another absolute maximum problem, it's a different function and the region might be slightly different, but it's always the same procedure. There's no variation of how you're supposed to solve this. Uh, Questions about this?
So whatever coordinate points we get for the individual sets, we plug it back into the original.
Into the original function, yes. Obviously, it would be consistent, like, for this edge, for this, like, for the point that you found, like 0, -1/2, for this particular point, you can use like the formula for the function coming from this point, because that's like, they are like kind of within the same case. But yeah, it's always better to just refer to the original formula to not like make any messes. Um, Any other question? Okay, so now we're going to do something a little bit different, which is the Lagrange multiplier method, which is a bit more interesting. And this is one that will be used for functions of three variables. So, okay, let's see. I do need to erase. Let me erase this part to give you some time to copy the rest. Okay, so let's talk about the Lagrange multiplier. So the way that we're going to think about this is like, we're going to find the max, let's say the max and the mean of a function when the function is defined, when the like when you only take the when you only care about the values the function takes, like say on a surface. So let me do like a more like a motivational example, and then you'll see from there what's the idea. So let's say you have like a function f, which again, like the best way to think about this is kind of like the temperature at the point x, y, z. So this function is giving you the temperature at any point in space. Okay, so like, if you want to be like a little bit like a bit of an exaggeration, but think about it kind of like the temperature for any point in the universe. Okay, so that would be f of x, y, z. And then you have like a surface. Okay, so you have a surface. Let's say you have like a sphere representing like the earth. So you have. You have the surface of the earth, right? And so since the temperature is since this function is giving you the temperature at any point of the universe, in particular, is giving you the temperature at any point of the earth, right? So you could ask for what is the what is like the hottest and coldest points on on the earth, right? Like, so where is F? What are the hottest? On the sphere. So that means I am asking what's the max and the mean of the function, but not everywhere in the universe, but rather just like on the sphere, right? So max. Okay. Is the question making sense? So again, like maybe if you again like think about it just like in terms of the solar system, maybe the hottest point is somewhere inside the sun. But we don't care about that, right? Like we only care about like knowing what's the hottest point on the earth, which probably will be in some desert or whatever, or inside a volcano, like surface of a volcano. And then the coldest point, right? So somewhere maybe in the Arctic or whatever. So you know, here you have to, it's a little bit different like from what we have been doing before. But kind of like there's a philosophy that you have to follow, which is which which is like if you I don't know if you remember this part, but when you have a function, if you're trying to find the maximum value, like this is related to this gradient descent video, if you saw already that like grayscale. But if you want to find the maximum value or the minimum value of a function, but let's just think about it in terms of the maximum value. If you want to find the maximum value of the function and I am located at a random spot, what I should do is kind of like find the gradient of the function at this spot, at this point where I'm standing, and then just move in the direction of the gradient. So for example, if the gradient is towards this direction, I should walk in this way, and maybe now the gradient changed, right? So I walk again this way, right? So the idea is like the gradient will always lead you in the direction where the function is increasing, is increasing most rapidly. So to reach a max, you have to follow the gradient. Is that making sense? So let's say I'm somewhere, I'll try to draw this. So let's say that you're somewhere on the surface of the earth and the gradient of this function, right? Oops, let me do it a little bit more exaggerated, more to let's say that the gradient of the function is pointing that way, right? So what's the issue there? That if you just try to follow literally, if you try to follow the gradient as I draw it, right, then you soon enough will exit the planet, right? Because if you follow this arrow, that will force you to leave the surface of the earth, right? Like there's no way to follow this arrow within while staying still on the surface. So really what you cannot just like when you are forced to move on the surface, you cannot just take the gradient as it is. Rather, what you want to do is kind of like, maybe it's easier to think about it like terms like in terms of like actual arrows. So imagine instead of like talking about the planet, let's say you're moving on the plane, right? And the gradient is kind of pointing this way. If you just follow this gradient, then yeah, like you would be somewhere outside the table. So what you can do instead is kind of like follow the direction of the gradient, but just like the part of the vector that's on the tangent plane. So you know, like kind of like this gradient makes a shadow on the table, a projection, and then you follow the shadow. So what I'm trying to say is that, this vector there's like a shadow of the gradient here, right? And that is something we can follow while still remaining on the surface. Is that making sense? So you can, like, my point is that if you just follow the, the gradient of the function, then you will exit the surface. You will need like kind of like a spaceship. But if you follow the shadow the gradient makes on the planet, then that's fine. You will remain there on the surface. So the idea is that when you move on the surface, you still want to follow the gradient, but the closest thing you can follow is not the gradient per se, but just its shadow. Is that making sense? So far, so good?
Is that the projection? Or
If you want to do, would call like a projection. Yes, yeah. Good. So it's still the same principle, follow the gradient, but instead of saying follow the gradient, you just say follow the shadow of the gradient. Okay? So now you're happy, you start walking along the shadow. So you get to the shadow. And then let's say that you got to the point that's the hottest point on the planet, right? So now we're here at the hottest point. Okay, so what does it mean to be at the hottest point? The point is that once you got to the hottest point, there can be no more shadow. Because if there were still a shadow to follow, then you just move in that shadow and the function keeps increasing, right? So once you get to the hottest point, the shadow needs to go away. Is that making sense? So here, the shadow must be the zero vector. Okay, so no shadow. So actually, I cannot even draw this like this. I have to put here no shadow to follow. Or shadow of size 0. Okay, but what does it mean for the shadow to have size 0? If you think about it, that doesn't necessarily mean that the gradient itself is 0, just means that the gradient has to be completely perpendicular to the surface. Because if you draw the gradient here perpendicular to the surface, right? Then there's no shadow to be made, if that makes sense. So that means that at a hottest point, right? At a hottest point, the gradient has to be a normal vector to the surface. Is that making sense? Sounds reasonable. And the same works for the coldest point, but it's enough just to think about it for the hottest point. So the point of the Lagrange multiplier method. So like what the Lagrange multiplier method says is that if you want, if you want to find the point, if you have a function, if you have a function f of x, y, z, and you want to find the large where the function takes its max and min values on a surface, and you want to find the gradient of the function will be the gradient of f will be a normal vector to the surface at that point. Gradient of f will be a normal vector. And this is like actually a very important method technique, and I'll see if I can find like an interesting video on YouTube for you to watch. But like this Lagrange multiplier method is kind of one of the most useful ideas of multivariable calculus. Will be a normal vector to the surface. This is like it also goes under different names like constraint optimization. That sounds a little bit more like let me put it. So that is probably a more normal terminology if you're trying to find like applications of this to other things like economics or like physics or like um computer science, whatever. So statistics, like that's probably the name under it, you'll find it. Because it's constrained because what this is saying is that you want the max and the mean of the function, but not anywhere in the universe, right? But only when you're constrained, when you're forced to be somewhere, you're being forced here to be on the surface of the earth. So that's what the constraint part means. So, so what I'm saying is that you have like this, so now here's like anyone remembers maybe from before, if I gave you the equation of the sphere, how would you have found normal vector to the sphere from this equation? There was a way that we already saw it.
By taking the gradient.
Right, exactly. So there's particularly, we already had a normal vector to this sphere, right? Which was the gradient of this function, right? Perfect. So what this is saying, what the Lagrange method is saying is that this gradient has to be essentially parallel to the other gradient. So there's kind of like two gradients at play. One is like the gradient of the function, right? And then there's the gradient of the equation that defines the surface. So in the Lagrange method, what you're looking for is for like the two gradients to be parallel. So let me write it like this. So and this is how usually this is written. So what you're trying to find is for the gradient of f to be a multiple of the gradient of the surface. So because parallel vectors mean that they're rescalings of one another. So that's usually the better way to write it. So let me put it like this. So this is the gradient of the function. And then this is like the gradient of the equation that defines the surface. And this lambda is a rescaling factor. That's a usual name that is given to this rescaling factor, which is called the Lagrange multiplier. So this is like a rescaling factor called the Lagrange multiplier. Okay. Yeah.
What's G?
G.
Yeah, like the.
Oh, sorry. G would be, for example, in this case, G is kind of like the name for the equation. So for example, in this case, G would be x squared plus y squared plus z squared equals 1. That name, you don't have to include the 1, like that doesn't matter. Because like those two would have the same gradient. Yeah, sorry about that. So G, like it just means like the function that defines the equation of the surface. No, but that's good, yeah. So what I'm trying to say is that there are two kind of like functions. One is the one that you really want to find the max and mean of. That's kind of like the temperature. And the other one is the one that determines the surface, which is what I'm calling G. That's kind of like the standard convention. So G is like the function that determines the surface. So this is like the gradient of the function that you're optimizing. Or optimizing and let's say gradient of the function defining the surface, but maybe let's put it like that. And yeah, these does have a lot of like this idea does have like a lot of useful applications. Um, I'll do first like a few examples about this, but let me check first. Are there any other questions before I continue? Um, okay, so here's an example. I'll do like example difference from the one on the videos. So in case you just want to have some extra ones. So because this is a method that's kind of useful to have like multiple illustrations of. So let's say that the function is like xy plus z. So I have this function. And I want to find the max and the mean value of this function on the sphere. So let's continue working with the sphere because we have talked about it so a bit up to now. So what is the max and mean values of this function? So here G is like, again, G is reserved for the function that defines the surface. So the surface here is the sphere. So G x squared plus y squared plus z squared equals 1. I mean, like the one doesn't need to be included, so it's just x squared plus y squared plus z squared. Because you want to think of the sphere like as a level surface for this particular function. Okay, so let's see. So what the method says is like find both gradients, like you compute both gradients separately, and you want to check where do these two gradients become parallel. So in general, the gradients will not be parallel, but at the max and the mean, the gradients will be parallel. Okay, so that's what we're trying to find. So let's see. Okay, let's use those colors. So what's the gradient of f? The gradient of f. Again, the gradient is derivative with respect to x, derivative with respect to y, derivative with respect to z. So the derivative with respect to x there is y. The derivative with respect to y is x. And the derivative with respect to z equals 1, right? And what's the derivative with respect, what's the gradient of g? We have talked about this one before, right? Like the gradient of g is 2x to y to z. Okay, so we want these two gradients, they don't need to be exactly the same, they just need to be parallel. Yeah.
Can you explain how come the GXY, it's a level surface? You said something about a level surface.
Right, so the thing is like, so the g is like a function of three variables, right? So itself is not a level surface. It's just that when you set it equal to 1, it becomes a level surface. So like x squared plus y squared plus z squared equals 1, it's like a level surface for g, right? What I'm saying is like g equals 1, right? The level surface g equals 1 is precisely the unit sphere, if that makes sense.
Yeah.
Okay, good. So what you want, so you want these two gradients to be parallel, right? So what is lambda times the gradient of g? That's 2 lambda x, 2 lambda y, 2 lambda z. Okay, so that, like, you just multiply the second gradient by lambda, that's like a convention, you could have put the lambda in the first one, multiplying the first one, but like, the standard convention is lambda to be multiplying the gradient of the surface. Okay, so what the method says is that you want these two things to agree. So those two things should be the same, but what does you need to have happen, like for that to occur? You need like every entry of those vectors to match. So what that means is that the first entry of each vector must be the same. The second entry must be the same. And the third entry must be the same as well. Is that making sense so far, second? So what makes this type of problems a bit tedious, honestly, is like solving the system of equations. So setting up the system is not too bad. What the equations that you need to solve are not too bad because it's just finding two gradients and set them equal to one another, basically, after doing the rescaling. What's a little bit long is to just like find the, the values for x, y, z. So it really depends a lot on the, on the functions that you're given, like how long this takes, but as I was saying, like, yeah, like on the recordings are a few other examples which are different from the one I'm doing here, if you want to check those out. And they're more like examples. There'll be, well, I guess not on tomorrow's workshop, but there's the one after, I'll post like some Lagrange multiply problems on for you if you want to check during the spring break, for you to do some more, plus the ones that are by that. But so in all these problems, you have to decide, what you want to solve for first, and there's not like a unique strategy for how to solve these problems. So there are a couple of alternatives. Like what seems a little bit easier in this particular system is that the last equation, like, the first equation involves two variables, x and y. The second equation involves two variables, x and y. Only the third equation involves a single variable. So it's kind of easier just to start with that one because of that. So you can solve, for example, you can solve the first equation for lambda if you like. Right, the third equation gives you the value for lambda in terms of z, and then you can plug that into the first two equations, substitute that into the first two equations. Okay. Okay, so if you substitute this into 1 and 2, you find that y equals 2 lambda, but lambda now becomes 1/2z, so the 2's cancel. So you get x z, and you get also that x equals y times z. Right. So, I mean, like, you don't need to be relabeled and renumbering the equations, but if you want, we can call these equations 4 and 5.
Not the x divided by z and y.
Oh my God, yes, thank you so much. So, like, you mean that the z should be here in the bottom, right? Good, thanks. Perfect. Thank you. Okay, anything else? Okay, now that you ask, how do you solve this? I mean, there are, again, a couple of ways you can do this, but I do prefer to have, actually it's kind of equivalent, but if you multiply it by z on both sides, you do have that y z equals x. It looks just a little bit better than the x z equals y. Now, actually, I prefer it that way. Okay. And so one thing you could do, for example, I don't know, it's like, say, substitute y, the y from this equation into the y in the first equation. So substitute 5 into 4. So if you substitute that, y is replaced with xz, so you get x z squared equals x. Does that make sense? Um, so that is what you get there. Okay. And then that's almost done. So how do you solve this system? Okay, it is attempting to just divide both sides by x. You have to be careful there, just because x could be 0. So in this particular, like for example, then you could ask, why didn't I have to worry about that here when I divided by z? The thing is like z cannot be 0 here because there you would get 1 equals 0. So then that's kind of clear. But it's not clear, like, I mean, here, like putting x equals 0, that kind of works on both sides. So it's not ruled out as in the other one. So a better way to think about this equation is as x z squared minus x equals 0. Kind of move everything to one side. And then you can say that this is x times z squared minus 1 equals 0. Okay. So that gives you two possibilities, which are like the ones that we were talking about. So you could get x equals 0 or z squared equals 1. So, and then these happen separately, they're in kind of like non-interfering cases. So whatever you find on the first case is different from what you would find in the second case. You can not use the information between the cases, okay? They're kind of like parallel universes, these Marvel multi-hero movies, like where like nothing, like although they're interacting. So here, like you really want to think that they're not interacting. So like nothing really, whatever you find in one case cannot be used for the other one. So for example, what happens if you assume that x equals 0? Y was given in terms of x and z, right? So y would become, which was xz. Like if x happens to be 0, then that forces y to be 0, right? And then you could ask, well, what else do we have? Well, we also have, like you might say, okay, so I already know that x has to be 0. I already know that y has to be 0. But how can you find the value for z? You have to remember then that like the point has to be on the sphere. So now we have to use that the point is on the sphere. So using that x, y, z belongs to the sphere. Well, since x and y are both 0, you get z squared equals 1. And then, yeah, now you're getting the z equals plus or minus 1, but not because like you use that information from here. You see, like it kind of came from for different reasons. So it's not, and at no point kind of like I added that by, I never added that by like, I never forced that into the equation. It kind of just popped out. So in this case, the options that we're getting for the critical points are 0, 0, and plus minus 1. I mean, so we're getting two options, right? And likewise, in this case, you know. Is that making sense? And then if, in this case, if z squared equals one, it's kind of like the same because the point since, because x, y, z is on the sphere, it's on the sphere, then you know that x squared plus y squared plus z squared equals one, but this is already one by assumption. So you get x squared plus y squared equals zero. So you don't find anything else here, like, because like the only way for two numbers to square to zero is if each one is zero. So I mean, you know, in both cases, like you get 0, 0, 1 and 0, 0, -1, but that's not kind of like the rule, like. So what typically will happen is that, like, what will happen is that, you know, like the points that you get from each case can be different. Sometimes one of the cases will not give you any options and another will. So there are other variations, but yeah, I'll refer to the videos. Like I have like 2 or 3 more examples which are different to this one, so you can check those out. I'll send you like the link to those videos, which are kind of like the usual Zoom meetings that I post at the end of every announcement. But so that means that in this, I'm almost done. So that means that in this case, like you have 2 critical points, and it's kind of, in this case, it's similar to what we did to the max mean problem from the beginning. So if the point is 0, 0, 1, this gives you 1, and if the point had been 0, 0, -1, this will give you -1. And so this has to, the North Pole in this problem is a max, and the South Pole in this problem is a mean. In other more complicated problems, you would have more than 2 points. In many applied problems, you'll see that as you work on the MyLab assignment on 14.8. What happens in many applied problems is it's actually there's only one solution. So depending on the problem, sometimes like there will be only like a max or a mean. That also can happen, but at least in the case of something like the sphere, there will be a max and a mean. And then that's kind of how you would find it. Yeah.
If there's only one solution, then how is there like only a max and not a min?
So what happens is that, okay, in the case of the sphere is similar to what we did at the beginning, because there, at the beginning, it was kind of like a finite region on the XY plane, right? The sphere is kind of like a finite, like it's a finite surface or like a surface of finite area, but you can have something like different when the surface is kind of infinite. So actually, this is one of the problems that's on the videos if you want to watch it, but let's finish with that because this is like a good question. So, for example, if you have a plane, here's another type of problem, which again is on a version of this is one of the Zoom videos that I'll send you. But if you have like a plane, let's say this is like a plane x plus z, x plus y plus z equals 1, right? If you have a plane, the thing is like the plane is infinite, right? It extends forever. So it does make sense for there to be like a point on the plane that's closest maybe to the origin. I don't think the point necessarily is here. Like let's just not be biased. Well, all the coordinates should be the same by symmetry. It will be, I think it's somewhere here. Like it does make sense for there to be a closest point of the plane to the origin, right? But so there's like a minimum to the distance of the plane to the origin, but since the plane is infinite, right? You know, you can always have points like that are further and further away from the origin. So the difference between this and the sphere is that the sphere being finite in some sense will always force you to kind of like return to like, you know, you cannot grow in size in both directions. Like, you know, you cannot become arbitrarily large or arbitrarily small. So when the surface is kind of infinite, that's in many cases when like, you know, only a max or only one mean will occur. Does that make sense? So no, but that's a good clarification. But yeah, so there is a plane problem If you want to think about it, yeah, so if you want to find, you're trying to find like the function. You want to find the point that's closest to, the point that's closest to the plane, and here, like, you could use like the distance function, like root of x squared plus v squared plus y squared, okay? And the constraint is g in this one. And so let me just like finish by writing out the system. So if you compute when you compute the Lagrange multiplier problem. Yeah, this one can actually be solved like in 2 seconds, because the gradient of G is very easy. In this case, it's just 1, 1, 1. And the gradient of F, well, it takes a little bit more time, but. Right, when you have it, and this is kind of what you get from the Lagrange system. And because every side is being equated to lambda, it doesn't take too much to convince yourself that the only way to solve this is for x to be the same as y to be the same as z. So the solution to this system of equations is for x to be y to be z. Okay, so that tells you that the coordinates need to have the same value. But then how do you find the actual value of the coordinates? Well, you plug it back into the equation of the plane. So that gives you, the equation of the plane was x plus y plus z equals 1. So you get 3x equals 1. So x equals 1/3, and that's the same value as y and z. So really 1/3, 1/3, 1/3 is the point on this plane that's closest to the origin, for example. Usually, like, yeah, the problems will have some sort of like symmetry in the formula so that it doesn't take forever, because it's like problems. If you used to work with like arbitrary, like random functions, then yeah, like the algebra is too tedious. But for something like this, it's kind of more like manageable, and you can kind of like see it by eye. But yeah, this is like a good example of where, there's only one mean, but no max. And the fact that it's a mean is kind of like more like clear from the picture, because it's a plane, right? It's like you can convince yourself that it should, that one could not be the max. Is that making sense? Okay, so I'll see you after the spring break, and again, I'll send you like some practice exams and other things throughout tomorrow and Friday for you to have, if you want to start working on that during the break. But otherwise, enjoy it, and I'll see you in 2 weeks.